Hello again, it's me, Professor Aaron Albert, coming at you with Lesson 4. Let's learn some econ. So today's goal is to introduce some of the basic concepts behind microeconomics. In short, we want to talk about what rationality is and isn't, what describes rational and irrational preferences, and then begin drawing some indifference curves and talking about what indifference curves do and do not make sense in accordance with our assumptions regarding rationality. We'll also talk about budget sets and how to map between budget sets and their graphical counterpart. So the first question we have today is an important one. Spend a moment, ask yourself, are people rational? Why or why not? Think of some good examples in your life where you think people were or were not rational. So the reason I began with a discussion of rationality is because to economists, rationality is really simple. Although there's a colloquial definition of rationality that includes things like being circumspect, not being emotional, not putting yourself above others, things like this. In economics, rationality is a specific word that means two very simple things. First, in economics, if rationality assumes that we are rational, we are saying that people's preferences are complete. By complete preferences, we just mean that consumers must be able to compare any two bundles. You can compare these bundles in three ways. Either I prefer A to B, I prefer B to A, or I am indifferent between A and B. And for the most part, this should be the case. If I'm able to offer you an apple or an orange, you can indeed compare apples to oranges. You either prefer an apple for an orange, or you don't care. As long as you are able to say prefer apple, prefer orange, or don't care, you have complete preferences, and you've met that requirement for rationality. The second component to rationality is transitivity. Transitivity is just saying that you cannot prefer A to B to C to A. So if we had I prefer apples to oranges, I prefer oranges to bananas, it better be that you also prefer apples to bananas. Otherwise, you create some sort of loop. And those loops don't make a lot of sense. The last thing we'll do is we'll assume something that is called technically non-satiety. That is, your preferences are such that you are not satiated in goods, i.e., more is better. If I have one apple and I could have a second apple, I'd prefer to have the second apple. Second apple is tasty. Second apple presumably could be sold for some money. And anything else, there's free disposal. If I don't like that apple, I can throw it away or give it to a friend. And so we should take a moment to think about how strong these assumptions are. Do we think that rationality is reasonable from the standpoint of what economists think rationality is? Think about that for yourself. Is it possible to think of times that your preferences have been incomplete? Is it possible to think of times your preferences have been intransitive? For the most part, I think that these are reasonable assumptions. Times my preferences have been incomplete. If you're ordering at a restaurant and the menu is not in your native language and you don't know what the options are, that could be time you're incomplete. You might prefer option 1 to option 2. You also might not know what either option is, and one of the options might be directions to the restroom. Transitive. For the most part, we think that adults with well-formed brains have transitive preferences. If you offer children choices, like really small children, you might find their preferences are intransitive. That is, they might prefer Snickers to Oreo and Oreo to Reese's and Reese's to Oreo. But they're also small people with not fully formed brains, so it's hard for them to hold all the information at once. And it is possible to get preferences that have satiety. In fact, it's really easy if you have bads. At any point in time, I am completely satiated in toxic sludge. I do not want toxic sludge. But it's really easy to turn that into a good by, instead of talking about toxic sludge, talk about the disposal of toxic sludge. So with this in mind, although it's popular to say, oh, rationality is incorrect and therefore economics is wrong, when economists say rationality, they just mean these very simple things that we should, for the most part, agree with. The next thing we want to do is talk about is a plane of your possibilities. Let quadrant 1 be given as thus, and picture that every point in quadrant 1 gives you the options between some number of pizzas and some number of burritos. And therefore, every point in this plane gives you a combination of those two objects. And we also can imagine that every single combination of pizzas and burritos gives you some level of happiness. The question we might ask is, well, let's say that you're sitting here at point E. Point E is specified by 25 pizzas and 15 burritos. Well, how happy are you at E as opposed to at all of the other points? Take a moment and work them through. How happy you're at E versus A, B, C, D, and F. So hopefully you noticed that there are at least two comparisons that are pretty simple. For instance, look at E and look at F. Which should be preferred if we assume that our preferences are quote-unquote rational? It seemed to me that we must prefer F because F has more of both pizzas and burritos. So by non-satiety, it must be that F is preferred to E. By similar logic, E has more pizzas and burritos than D, therefore E must be preferred to D. Yeah, more stuff. It gets more complicated when we look at points like C, A, and B. What do you think people prefer? Do they prefer C or do they prefer E? Well, the answer is it depends. If we compare C and E, at point C we have fewer pizzas and we have more burritos. So it really depends on which you like more, the burritos you're gaining or the pizzas you're losing. Similarly, if we look at points A and B, at points A and B, we've gained pizzas and lost burritos. So someone who loves burritos will say that's a really bad deal. Someone who likes pizzas will say it's a good deal. So just using completeness, transitivity, and more is better, we can say that all these points are comparable, and the points that have more stuff must be preferred. However, that only gets us some of the way. In order to really start making comparisons across this plane, I'll introduce an additional object. We'll call this object indifference curves. Indifference curves are defined as curves that show where you are indifferent. That is, comparing points C and E and C and A, it must be that I am indifferent between C and E, and I am indifferent between E and A. This is really useful because if I look at that indifference curve, I now know how to compare points A and F and C and F. Take a moment and think it through. Why might it be that I prefer F to C? And why might it be that I prefer A to C? So all we have to do is look at what's given by our indifference curves. First, note that F must be strictly preferred to E because more is better. Second, we know that C must be indifferent to E because they're on the same indifference curve. Therefore, although F has fewer burritos and more pizzas than C, it must be strictly preferred because F is preferred to E and E is indifferent to C. So indifference curves allow us to compare a lot of points that used to be incomparable. However, we must ask ourselves, here is one indifference curve connecting points C and E and A, but could I have drawn this indifference curve in some other way, perhaps connecting other points? The answer is obviously yes. There are infinite ways that I could draw this indifference curve, just like there's infinite ways that you could have preferences between pizzas and burritos. Again, the indifference curve just shows all bundles that an individual consumer likes equally well, and they could have all sorts of different preferences. However, although their preferences could look all sorts of different ways, we should take a moment to pause and think about what things must be true about their indifference curve. The first thing that we assume is that if we have sets of indifference curves, their indifference curves are improving to the northeast. That is, the indifference curve containing C, E, and A must be preferred to all points on the indifference curve containing B. Why is that? Well, that must be due to non-satiety. We can perform the same exercise we did a few slides earlier. If I want to compare point C to point B, you'll note at point B I have more pizzas but fewer burritos. And so it's a little confusing because we can't really tell. But due to the indifference curves, you'll note that A must be preferred to B because A has strictly more of both, and C is indifferent to A. Therefore, by transitivity, B must be less good to me than point C. Therefore, moving to the northeast on your indifference curves must be better. Our indifference curves must be parallel lines increasing this way. Our next question is, well, could we have chunky curves? Could we have curves with some width to them? Is this rational or not? Take a moment, think it through. So we can apply the same tools we just used. You will note by this indifference curve, point A and point B are preferred how? How might I compare point A and point B? Looking that they are on the same indifference curve, they must be indifferent. So we know that A is indifferent to B, but also if you look at the curves, A has strictly more stuff than B, so by non-satiety it must be that A is preferred to B. However, if I note that A is preferred to B, and A is indifferent to B, those can't both be true. That is a contradiction, therefore those preferences cannot hold. Another thing you might wonder is, well, I've mentioned previously that your indifference curves will be parallel lines improving to the northeast, but why do they have to be parallel? Could they cross? Take a moment, think it through. What is or is not wrong with crossing curves like I have here? So if you look at these crossing curves, I can perform a lot of the same operations that I have done previously. You'll note that A and E are on the same indifference curve, so it must be that A is indifferent to E. You'll also note that E and B are on the same indifference curve, so E is indifferent to B. By transitivity, you will note that A must be indifferent to B. What's wrong with that? Well, if you note, A has strictly more stuff than B, so A must be preferred to B. And then again, we have a contradiction. It can't be. Your indifference curves cannot cross. That will cause problems each and every time. Another thing we might ask is, well, what if my curves are upward sloping? Before, we had parallel lines that looked like this, but what if I instead rotate them so that they slope upwards, not downwards? What's wrong with this? Well, this one's really simple. The indifference curves directly tell me that D is indifferent to E and indifferent to F. However, you'll note that E has strictly more stuff than D, and F has strictly more stuff than E. Those points cannot be indifferent. Therefore, upward sloping curves are incorrect. We will never draw indifference curves this way. Another thing we will note is that I have not drawn indifference curves that are concave upwards like this, that bow up. I will say that this does not strictly violate any of the rules we've been given, but we will tend not to draw indifference curves this way. Look at these indifferent curves and think about what these suggest about our preferences, what these suggest about the way we prefer bundles. So the interesting thing about these bundles, and the reason we'll often not use them, is because they start to encourage weird behavior. This says that C, where I have lots of burritos and very few pizzas, is indifferent to B, where I have lots of pizzas and very few burritos. But look where point E lies. Point E lies between C and B, but slightly northeast of the straight line. This straight line tells us if I were to exchange pizzas and burritos at some sort of reasonable ratio given my preferences, you would expect that I'd be happy with this point. It lets me get a more intermediate bundle with a mixture of goods. These preferences say that I would not accept some sort of nice mixture of goods. Instead, I want to have either mostly all pizzas or mostly all burritos. And we mostly find that people mix. I rarely see people at the grocery store with a cart just full of burritos. They get sick of burritos really fast. This is not all of the different types of indifference curves we could have. In fact, there are an infinite possibility of ways to draw indifference curves. However, we will often look at some things I call the usual suspects. Two of the usual suspects are on this slide. We have preferences for Coke and Pepsi on the left, and preferences for pie and ice cream on the right. Spend a moment and tell me how you would describe these preferences in words. And by that I mean, what kinds of bundles do you prefer, and how do you choose among these bundles? So this, you hopefully noticed, suggests that Coke and Pepsi are substitutes. Do I care whether I have Coca-Cola or Pepsi-Cola? No. I just want to have cans of cola. I am indifferent between one can of Coke, one can of Pepsi, or half a can of each mixed together. Similarly, I'm indifferent between 2 cans of Coke, 2 cans of Pepsi, or 1 can of each. These are perfect substitutes because I can perfectly substitute between Coke and Pepsi. I don't care which I have as long as I have one of them. And as before, you'll note that my indifference curves are increasing to the right, they're downward sloping. All the other rules are obeyed, with the exception is that they don't concave downwards. These are just linear lines. The other ones we had are what's called perfect complements. Picture you're at point A, where you have 1 scoop of ice cream and 1 slice of pie. Do you get more utility by increasing the amount of ice cream you have? Strictly speaking, no. A is indifferent to D is indifferent to E. Why? Well, my preference tell me that I really don't like ice cream and I really don't like pie. I only like the combination of the two of them together. So the 2 items are perfect complements. I'm behaving optimally when I'm at the vertex of these lines, i.e. when I'm at A, or B, or C. Because if I'm at any other point in this quadrant, I'm throwing stuff away, right? Like, I am just as happy at D as I am at A, because at point D, I eat 1 scoop of pizza, 1 scoop of ice cream, 1 slice of pie, but I also throw away a scoop of ice cream because it didn't fit my perfectly complementary bundle. The last thing we might want to take a moment and think about is, what do budget sets look like? Let's assume for a moment your budget set is given by the price of the first item is $1, the price of the second item is $2, and you have $50 to spend. Using your X and Y axis, draw for me your budget set, i.e. what combination of items can you afford to buy? Well, if I were to do this, I would note that I can afford up to 50 units of good 1 and up to 25 units of good 2. So this must be the intersections on your axis. And then how can you trade off between those items? Well, it looks like a constant trade-off of 1 good 1 or 1/2 of good 2, i.e. a 2-to-1 ratio. So this downward sloping line should be at a slope suggesting that trade-off. I would come up with something like this. I can eat up to 25 of good 2, or 50 of good 1, or anything in between. Now my question is, could I afford anything else other than what lies exactly on this blue line that I've detailed? Yes. You also could go to the store and buy absolutely nothing. So we'll say your budget set is this whole triangle bounded by the diagonal line whereby you're spending your full amount of money. That's all we have time for today. Thanks so much, and see you next time.